In this lesson, we're going to go over how to use the five acceleration equations. In the last lesson, I showed you how to get them or how we derive them, but in this lesson, I'm going to show you using three examples on how to use them. Okay, first off, it seems very complicated because a lot of you are wondering, I don't know which formula to use. How will I ever know? Well, it's actually really easy. Picking the formula is actually not the hard part. It's actually writing down what variables you have. That's the difficult part. All right, so how many variables do we have? Well, we have V1, we have V2, we have A, T, and displacement. These are the five variables, and you'll notice that there are five equations. That's no coincidence. Also, you will notice that each formula is actually missing a variable, or like they kind of completely ignored it. So I'm going to have a column here called my ignore pile. Okay. I'm just going to write down the variable that you just ignore or that's not in the equation. So in this first equation, you will notice that displacement is ignored. Also, you'll notice in the second equation, the final velocity is ignored. The third one, the initial velocity is ignored. The fourth equation, acceleration is ignored. And then the last equation, time, is ignored. And so essentially, when you solve for a question, you're going to actually pick the equation that completely ignores that variable. And that will help you limit which equation you should use. All right, we have our first example. We have a ball rolling down a hill and it covers 10 meters in 13 seconds. So I've got my ball and the hill is actually 10 meters long and it takes 13 seconds to get to the bottom. If the ball started from rest, so here's the ball starting from rest, how fast will it take how fast actually will the ball be traveling at the bottom of the hill? All right, so that's all the information we have. Now, if you attempt to graph this, you can't. All right, it's pretty hard to graph this. You could try to draw a velocity time graph. You know V1 is at rest, or you know it's got 13 seconds, but trying to graph a perfect triangle that has an area of 10 meters is a little challenging. So this is difficult. You can't graph this, or it will be hard to graph. Cannot graph easily. Okay. And so this is where we actually use our one of the five acceleration equations. First off, what you need to do is you need to list your variables. All right. Every time I start a question like this, I always list the same variables over and over and over again like this. You don't have to follow the same order, but it's just out of habit for me, V1, V2, D, A, and T. Okay, and also a little picture of the question, a little drawing or sketch also helps with the understanding. All right, now that I've listed my variables, let's fill what you know. V1, it's starting from rest, so that should be 0. V2, that's what you are solving for. That is the question. So I like to leave a question mark there. D, the displacement, that's 10 meters. All right. Acceleration, I have no information on that. And then the time is 13 seconds. Okay, so now you have your variables. You'll notice that the acceleration, there is no information on it. In fact, we've completely ignored it in this question. So I like to put an X through it just to keep in mind that I have no information whatsoever, but I don't need to solve for it either. And therefore, if I look at my 5 acceleration equations, I can completely ignore the acceleration, and I'm going to use equation 4 to solve this question. So let's use equation 4 to solve this question. V1 plus V2 divided by 2 times time. All right, plug everything in. This is 10. V1 is 0. V2 you're trying to solve for, 2 times 13 seconds. I'm going to multiply that by 20 or by 2 to get me 20. The 0, obviously, that I can ignore because 0 plus V2 is still V2 times 13 there. I'm going to bring the 13 over to the other side, and this is what you're going to get. V2 is equal to 20 divided by 13. So what I did is I brought the 13 to the other side, and I switched left and right just to make it a little easier. And I think that's about it. Yes. That is going to be 1.5 meters per second, and it's going down the hill. Down the hill. And there you have it. Pretty easy, I hope. Let's try another one. All right, here's the next question. You are traveling at 90 kilometers per hour east when you see a stalled car 100 meters in front of you. A lot of you are learning how to drive, and what a stalled car is basically a car that has stopped, that cannot go. Maybe it has a flat tire, maybe the engine's broken down or overheating, but basically it's stopped. You instantly hit the brakes. So we're going to ignore reaction time, which we will talk about in another lesson. So we're going to instantly hit the brakes, which is kind of impossible, but we are going to now slow down at 5 meters per second squared. Will you hit the car? So there is a yes and no component to this question. If yes, how fast did you hit it? And then if no, where did you stop? So how far away were you from that car? All right, so let's list our variables again. V1, V2, DAT. Perfect. Okay, so there's our variables. We are initially traveling at 90 kilometers per hour. So 90 kilometers per hour, and we are headed east. Okay. So then we want to stop. All right, so let's stop to avoid this thing. And let's continue. And the acceleration we have, oh, the car has stalled. Oh, let's see, we have lots of information here. I'm going to actually leave the car is stalled at 100 meters in front of me. Let's leave that blank for now. Okay, we do want to stop, and let's say we slow down at 5 meters per second squared. Now, when you slow down, remember that acceleration lesson a couple lessons ago? It has to be negative because we're slowing down. So in other words, it has to be 5 meters per second squared west, right? If you're traveling east, so let's say if you're traveling east, which is this way, to slow it down, you've got to push that way to slow it down the other way. So basically, the acceleration here is going to be negative 5 meters per second squared, technically east, okay, or west. So you've got that negative 5 in there. The time, um, let's see, I don't have any information on the time. That's correct. I don't. Okay. So I don't have any information. We've completely ignored time. So let's actually X that out. And if I put 100 meters for the car, that means we have nothing to solve for. So that doesn't make sense. Let's figure out where it stopped. Okay. So we're going to assume it stopped, and we want to figure out where. So here's our question mark. If we leave this as a question mark and we solve for it, then we can figure out whether or not it hit the car. Okay, so Before we continue though, let's take a look at our units again. We're okay with the -5 because it's slowing down, but 90 kilometers per hour is not acceptable. We need to convert that. And when we convert that, we're going to turn that into 25 meters per second. Okay? All right, now time is missing, or we can ignore it. And if you go to the ignore list, you will notice we are going to use equation 5. All right, so let's use equation 5 over here. V2 squared is equal to V1 squared plus 2AD. All right, let's plug everything in. This is going to be, this is going to be 0. This here is going to be 25 squared plus 2 times -5 because we're slowing down, and we're going to solve for d. All right, so when you solve for d, hopefully your calculation, this will be 625, that's 25 squared, by the way, divided by 10. Okay? And you'll notice the negative cancels out because when you bring this to the other side, it's negative 625. Anyway, this is hopefully what you end up getting. All right? And then you're going to get 62.5 meters. So the car took 62.5 meters to stop. This is less than 100. So therefore, no, it did not crash. No, it did not crash. And there you go. All right, last example. We're going to throw a ball, and we're going to go throw the ball up at 10 meters. And when will the ball land back in your hand? We're going to assume no air resistance. So I guess we're doing this on the moon, where there's very little air resistance, or in a vacuum. And then hopefully you have an air tank to keep you alive because you can't breathe. Anyway, here we are. Now, when you throw the ball up, is the ball slowing down or speeding up? Well, you know it's slowing down, and then it reaches max height, and then it speeds up. So there is actually acceleration, and that's called gravity. Gravity speeds things up or pulls things back to the ground. And so this is something that you need to assume in all things that are falling, or yes, pretty much falling through the air. All right, so the acceleration due to gravity is 9.8 meters per second squared, and it's down. All right, some of you are going, where did you get that number? Well, that number we just measured through experiments. Okay, so a bunch of readings are taken, and this is sort of like the average. And this is basically how fast anything falls through the air, or not through the air, through the Earth's gravity, assuming that there is no air. And so, therefore, it's almost 10 meters per second every second. That's how much faster things fall when it's falling due to the Earth's gravity. Notice I said down. All right, so obviously, when you drop anything, it's going to be pulling down, not pulling up. Later in class, we might be able to measure this value of 9.8 so you can confirm, yes, indeed, this is the correct number or acceleration for gravity. Okay, so let's list our variables. V1, V2, D, A, and T. All right, let's start. V1, the initial speed is you're going to throw the ball at 10 meters up. Now, I know a lot of you thinking, oh, I have the ball here, okay, and it's starting at 0. It's not going anywhere. That's not true. I don't want the pushing part, Okay, that's not the part I'm looking for. The part I'm looking for is once you finish pushing and then the ball is now flying, like you're not touching the ball, that's the speed I'm looking for. Okay, so this initial speed is 10 meters per second, right? This is after the push. We will deal with the pushing part in the next unit called dynamics. All right. Now V2, when it comes back down, it's going to land in your hand, okay? We do not want V2 up here, all right? This V2 is actually not zero, not zero. This is really, really, really important, okay? Because when the ball lands in your hand, it has a certain speed. Then your hand stops it from moving. Again, that detail we're going to learn about pushing the ball up to throw it or catching the ball. That will be in the dynamics unit. All right. Now, some people are not convinced. And how I can try to convince you is instead of a ball, let's do a bowling ball or a big boulder. Try to catch that. That's kind of heavy and hard, okay? And when you're catching it, you're going to feel it with a certain speed, and your body or your hand is going to catch it and slow it down, all right? So keep in mind that when you throw this ball, this does not include throwing or catching, okay? The ball does not include throwing or catching. Okay, the only part in this question is the part that you are not touching the ball. You're not physically touching the ball. So it only includes the part when it's in the air only. Okay, so in the air only. In the air only. And so therefore, when it leaves your hand, it has a speed. And just before it touches your hand, it has a speed. When you're catching it, that's when you slow it down to zero. Again, that's in the next unit. So in V2, that is not zero. That's really important. Now keep in mind, if you're looking at this, where is V2 zero? Well, V2 is actually zero at the very top. It's zero there because what happens is the ball has to slow down to a stop and then speed back up or speed up back down towards the earth. So basically you slow down to a stop, then speed backwards back to the earth. Okay. Um, let's figure out displacement. Ooh, displacement. Well, where did it start? It left your hand, and where did you catch it? Were you going to catch it right at your hand? So technically, the displacement is zero. It went nowhere. All right. Acceleration, in this case, it is 9.8 meters per second. Often, when you do these types of questions, we will not tell you that there is gravity. You have to recognize that this is falling. And so every time there's a falling type question, you must include gravity. Okay? So always include in every falling question. However, without air resistance. Without air resistance. If there's air resistance, then don't include it because it's falling slower because the air is slowing it down. Okay? All right. Now, other things I need to point out is that gravity is down, like I said, and we threw the ball up. Okay, so therefore we've got to make sure our signs are correct. I'm going to denote that this is going to be a plus 10 meters per second, and this here is going to be minus 9.8 meters per second squared because they're going in opposite directions. All right. Remember in physics The negative does not mean smaller, it means the other way or the backwards situation or the opposite direction. So keep in mind that plus we decided will be up and negative is going to be down. Okay, so time. Oh, that's the question. We are solving for time. All right, so we got our list of variables. And like I said, this is the tricky part. Once you got this labeled correctly, then picking the equation is the easier part. So which part is missing? Well, technically, V2 is the one that is missing. So let's go over here to V2 that is missing. And oh, look, we're going to do equation 2. So here is equation 2. Half AT squared. Perfect. Okay, this is now 0. This is now going to be 10t plus a half times negative 9.8 t squared. Or in other words, 10t minus 4.9 t squared. I can cancel out my t's and solve for it, or I can use the quadratic equation. Oh dear, does anybody remember that from grade 10 math? Well, if you always wondered why are we learning this quadratic equation, it's because of this course, physics. Of course, everything is for physics. All right, so I'm just going to rewrite the equation that I just have over here on this page. There. All right, so I've rewritten it over here. Okay, so keep in mind you can solve it in 2 different ways. Remember the quadratic equation? In grade 10, you used it to solve, okay? And then in this case, you could use this equation, b squared plus 4ac over 2a. That's one way to solve this equation. Now some of you are going, wait, miss, this looks nothing like this. Well, you got to rearrange that equation. So instead of this, which is math, what we do in physics is rewrite it like this. At squared plus bt plus c equals 0. All right, and look, you have your t squared, you have the t, and c is equal to 0 in this case. All right, so that's one way you can solve it. When you solve it, you will get 2 answers. T is equal to 0, and then comma 2.04 seconds. All right. Now, some of you are like, oh, I don't want to do that technique. Well, lucky for you, C is equal to 0, so I can do this instead. So this is a different technique. And honestly, I don't care what mathematical technique you use, as long as it's mathematically correct, I'll accept it for full marks. So here I've rearranged it to look like this, almost a standard form. You'll notice that C is 0. But what I'm going to do is I'm going to move T, or actually 10t to the other side. When I do that, one of the t's cancel out, so that cancels out and that square cancels out, and I get 4.9 t is equal to 10. And therefore 10 is equal to 10 divided by 4.9, which is equal to this. So now you have 2 solutions, which totally makes sense because when was the ball in your hand? At the start and at the finish. So this here shows you all the possible solutions, or exactly when the ball is in your hand. At the start time, the ball was in your hand at time 0, and this here is your end time. So how long did it take for the ball to land in your hand? Time is equal to 2.4 seconds. And there you have it. I hope that makes sense. Contact me if you have any questions. Otherwise, have fun with those 1D kinematics questions. Bye now.